One.
Hi guys. My name's Danielle,
I'm Maddie.
I'm Chris.
and today we are going to be talking about the science behind the MRI and the use of magnetic fields in the medical field. So today we're going to start off and talk about what is an MRI. Then we are going to talk about how magnetic fields are even produced by MRI machines. Then we're going to go into different levels of depth about what is the quantum physics behind the MRI that makes it even possible. And lastly, we're going to talk about how the MRI records signals and information to transmit them into our beautiful pictures we see today. So first off, what is an MRI? As many of us know, not everyone's in the medical field, but majority of people have gotten an MRI before in their life. So a magnetic field resonance imaging is what the MRI stands for. And it is a form of non-invasive imaging using magnetic fields and radio waves together to create a detailed image of soft tissues such as organs, arteries, and tendons. This was created because even though we do have x-rays, we're unable to see soft tissues in x-rays, and this allows us to take a deeper dive into the body without having to do any sort of surgical or radioactive procedures. And a little fun fact, did you know that about 100 to 150 million MRIs are taken annually across the globe, which is a crazy statistic. But out of those total, 40 million are produced by the USA alone, which I think it makes it even more important to see how quantum physics is used in our medical field today.
Now that we have an understanding of what an MRI is and what it's used for, now we can take a closer look at how the machine actually is able to generate such a powerful magnetic field that makes imaging possible. So, at the core of every MRI machine is a superconducting magnet. These magnets are the powerhouse of the system, and they rely on some pretty amazing physics in order to do the job. To function properly, they need to be cooled to extremely low temperatures, usually around negative 452 degrees Fahrenheit, or that's equivalent to 4 Kelvin. And interestingly, that's only a few degrees above absolute zero. And it's done using liquid helium, which allows the coils to enter a superconducting state. The magnet itself is typically made from a special alloy, niobium titanium, which becomes superconducting at these ultra low temperatures. And when in this state, an electrical current can flow through the magnet's coil indefinitely without resistance. That's what superconducting means. Zero resistance equals zero energy loss. And this is what allows the MRI to produce a very strong and stable magnetic field around the patient during the entire scan. And to give you an idea of how powerful this is, a standard MRI used in hospitals typically produces a magnetic field of around 1.5 Teslas, although there are some machines that go up to 3 Teslas for higher resolution. In comparison, that's about 60,000 times stronger than the Earth's magnetic field. The field lines run longitudinally through the bore of the machine, so essentially from the head to the toe of the patient, and their primary role is to align the hydrogen protons in the patient's body. So, because the human body is mostly made up of water and water contains hydrogen, this alignment creates a foundation for the imaging process. Now, MRI machines don't just rely on one type of magnet. They also use a gradient coil, which are additional electromagnets layered into the system. And these coils generate typically temporary and weaker magnetic field that are used to localize where the signal is coming from inside the body. And essentially, they help the machine figure out not just it's detecting, but where it's coming from as well. And lastly, you'll hear us mention sometimes RF coils or radio frequency coils. And these are responsible for emitting pulses that disturb the proton alignment and then collecting the energy that's emitted when the proton returns to equilibrium. But we'll dive deeper into how that works in the next few sections. So generating the magnetic field for MRI imaging isn't just about turning on a magnet, but it's essentially about creating an entire superconducting environment where powerful, stable, and precisely controlled fields are able to interact with the body. And this is the foundation that makes the next steps in the imaging process like signal generation and detection possible?
So, speaking like Chris had talked about magnetic fields and how that works in order to detect disease in humans, and from pulsing is working under how do MRIs work to detect disease. So, we use hydrogen nuclei because they have both a high amount of water and fat in their atoms. And they also have a low energy threshold, meaning that we can manipulate them in order to help our MRI work at a low with using less energy. So this is significant because, as the previous slide said, when the body's put in a strong magnetic field, the proton axes line up, and when radio frequency waves are added, this causes the hydrogen to be able to resonate. So, as you can see in the pictures, the top right picture, the hydrogens, typically their atoms are spinning like the Earth's axis, but whenever an electromagnetic field or a magnet is applied to that, the hydrogen protons axis line up with the magnetic vector, allowing us to like create a little bit more of like a enclosed space in order to have these pulses that Chris had talked about earlier. So, this causes the hydrogen to be able to resonate. This resonates at different parts of the body at different frequencies. So, when the radio frequency is turned off, a signal is created that allows us to plot certain intensities and begin a base picture of our MRI. Our MRI then uses radio frequencies to generate a series of pulses, as Chris said, directed at a certain part of a body at a time to see how long it takes the protons to relax. So, it's a series of pulsing and then relaxation. Since different parts of the body will generally take different amount of times to relax, these pulses are measured both in sections and in two ways, T1 and T2 relaxation, which T1 relaxation is when the magnetic vector is at its resting state, and T2 is when the axes are back in their normal resting state. So one of them is the electromagnetic resting state, and the other one is whenever the hydrogen protons are in their resting state. As a result, T1 images highlight the fat in the body, and T2 images highlight fat and water in the body. These are both important because we need to be able to isolate and remove the fat from our frequencies in order to just detect abnormal phenomenon. This helps us detect diseases because diseases are related to water content, such that more water in an affected area indicates disease. So that's why we have professionals like radiologists determining what the difference between different diseases look like on an MRI.
Now we're going to go into a little bit more depth about the physics behind an MRI.
So, one of the ideas that the first things that predated an MRI as we know it is nuclear magnetic resonance. So, just a little bit on the history of that before Danielle takes us away with that is that nuclear magnetic resonance (NMR) was discovered in 1940 by Felix Bloch and Edward Purcell. This was two independent discoveries just at the same time. And this principle of NMR states that certain types of nuclei, which in our case, for our purposes, is hydrogen, can absorb and emit different radio frequencies when placed under a magnetic field. This allows us to detect our diseases by applying magnetic waves to hydrogen protons, which emit certain frequencies based upon the amount of water or fat at a certain area, as mentioned in the previous slide. And different kinds of nuclei can interact with these radio frequencies under a magnetic field, which is related to quantum physics because this is done by manipulating the atom's quantum spin, which Danielle will talk a little bit more about.
So sometimes we hear the term spin being applied to quantum physics, but we truly can appreciate spin in this case because it is the heart that drives the production of an MRI. So we are going to take a step back and first talk about electrons and protons. Electrons and protons are both quantum particles that we can see in the nuclei of atoms. And like Maddie said, in this case, we're looking at hydrogen. And each of these quantum particles have their own electric fields that they produce with a north pole and a south pole, which I'm going to be referring for the rest of this video as dipoles. As these dipoles flip around in their natural state, they control the spin of the electron either counterclockwise or clockwise. As you can see here in our little exemplar photo, when the south pole is pointing up, the electron is spinning counterclockwise, whereas if it were to be flipped and the north pole was facing up, we have the electron going clockwise. So spin is just an intrinsic property that all quantum particles possess that when in the presence of a magnetic field, pardon me, they are able to rotate upon by these dipoles in either 90-degree quanti or 180-degree quanti, or better known as angular momentum vectors, which Maddie will get more in depth to in just a second. But because of the use of the magnetic field, we are able to manipulate these dipoles, and we are able to make two different orientations. We have an orientation called spin up, where these magnetic fields or the dipoles are in line with the magnetic field surrounding them, and they go to something called a ground state. Ground state just means that this particle or electron or proton, in this case, we're going to be focusing on protons, are at their lowest energy threshold where n equals 1. Whereas if we were to make them parallel with the parallel field like this, they would actually counteract the magnetic field and it would be called spin down. This is a way that particles are able to gain more energy and become excited once again. So spin mills the whole thing here, and spin is actually what we're measuring this entire time when we're producing MRIs. Without spin, we would not be able to have NMR or MRIs. Now, NMR allowed us to measure spin and we we're able to quantize it. However, we are not done yet. MRI is not complete because this is not the final product, because we are not able to apply this just to solids. We need to see how this manipulation of the spin of our atoms is relayed in a liquid, such as the water content in our bodies.
So, asking the difference between what we had just talked about and like the magnetic resonance that we know that actually works for MRIs is the nuclear spin systems. Quantum movement is the difference between not being able to do the things that we do with MRIs and this. So, and overall, what we're doing here is that we are rotating our magnetic fields and passing the current through coils, and the protons, the hydrogen protons, respond to the specific radio frequencies based on where in the body the magnetic field is and its strength. So an example here, the picture that we see, both of the blue things on the side are our dipoles, as Danielle had mentioned. They're both equal and opposite charged magnets apart from a different distance. And in the middle is our coil, and then our side are some extra magnets as well. So what we're talking about is our MRIs function on quantum physics. So specifically the properties of subatomic quantum particles, as in the property of spin, the change in the angular momentum from manipulating the dipoles. So what that means is angular momentum is a measure of how much an object is rotating, using like magnitude and direction, which is basically inertia and velocity. So inertia is an object's tendency to like resist changes in movement, and velocity is the rate of change of the object's position. So those two things are making up our angular momentum. So they're similar to momentum, as in you're going straight ahead and you're not moving and you're going at a certain speed, a certain direction. Very similar to that property, except this is rotational. So we're rotating our atoms, or spinning them, as Danielle had mentioned, either straight or perpendicular like this, in order to say like the magnetic waves, in order to have them pulse the way we can to detect disease. So one of the reasons that this is possible for us to manipulate these spins to help us detect our diseases and have these electromagnetic pulses is the Zeeman effect. So the Zeeman effect splits spectral lines, bands of lights, and the Zeeman effect sort of allows us to, like, as if it's a ladder, climb the rings of energy levels. So as we manipulate the angular momentum of the dipoles, and they allow us to take away or add or take away energy of certain particles. So we can split delta E, which is also energy levels of hydrogen, because of the presence of a magnetic field. So the Zeeman effect overall, in the presence of a magnetic field, allows us to split the energy levels of atoms. So either climb up and have more energy, or have a little bit less, like break it up into different amounts. Because we're in the presence of a magnetic field. And so we're allowed to only do this because of this effect. So that sort of runs our ability to have this quantum mechanics do this.
Another important quality that we see because of the Zeeman effect is that these orientations and these levels of energy, they're all going to be quantized, which we learned in lecture means that they must be whole real numbers. For example, when we were giving examples of the degrees that these dipoles rotate upon, it can be 90 or 180, whereas the energy levels can be n equals 1, 2, 3, etc., all the way up. And this means that there is no such thing as a partial orientation, as a part spin up and down, or a partial degree reading, or partial energy level. They must be whole real number in order to align with the Zeeman effect. So we're going to go a little bit deeper on another level into the physics on a quantum level behind the MRI, my apologies. So when you're laying inside this MRI machine, these magnetic waves are passing through the soft tissues of our body, and they are going to force the hydrogen in our bodies to align with this magnetic field in the poles or dipoles in this case, as we had said. In this case, the MRI is sending us down to a foundation of n equals 1 to a ground state in order to watch the amount of energy or signaling, which we'll get into more in a second, that these hydrogen atoms release and produce. In this case, we are going to look at something called NMV, which is known as the net magnetic vector. This is simply measuring the angular momentum in the vector that it takes to go from an energy state from low energy all the way back to a higher energy, which is produced by the magnetic field. And the time in between these two is also known as the spin lattice relaxation time. These are common terms used in radiology when discussing MRI because it can tell us what type of tissue we are actually looking at. Now, we know that the magnetic fields actually set us all the way back down to the lowest energy rung possible. How do we re-excite these hydrogen protons in order to receive this signaling? That would be where our radio waves come in that we have been talking so much about. Now, we're going to put all the pieces together and tell you how MRI is done from start to finish. So first, we go back once again to those magnetic waves, and they align our hydrogen atoms to a spin-up orientation or parallel with that magnetic field and set the energy level down to the lowest energy level possible. Next, radio wave frequencies come and disrupt this magnetic field in this orientation by exciting the protons or allowing them to gain energy. That energy is going to allow the energy levels of those hydrogens to increase to an excited state. However, this excited state is much higher than the relaxed or the original state of this proton. And because they're not in their original state, that means that they are completely unstable and they want to get back to stability. In order to do so, they slowly release energy until they are back to their original state. And we measure that in the spin lattice relaxation time and by the energy signal. That spike in energy is the release of energy that is picked up in by the coils in the form of a signal, which then we can actually relay into a picture as we see here as our example here on the right. So truly, MRIs are just the amount of spin that we pick up from certain cells in our body. And without spin, none of this would be possible.
So now that we have the magnetic field in place and the hydrogen protons in the body are aligned, how exactly are we able to measure what's happening inside the body in order to create an image? This is where radio frequency pulses or RF pulses come into play. So when a patient is lying inside the MRI scanner, the machine first uses that powerful magnetic field to align the hydrogen protons in their body, as we've already discussed. Then in the RF coils, the RF coils deliver a burst of energy into the body. This pulse is carefully tuned to the exact frequency that will excite those hydrogen protons. So in other words, the energy causes the protons to absorb just enough energy to move out of the alignment with the magnetic field. And depending on the settings that they are using for the MRI, they can either be flipped by 90 degrees or even 180 degrees, temporarily disorienting them. So after that short burst, the RF pulse is turned off. At this point, the proton starts to relax and realign themselves back with the original magnetic field. As they do, they release energy, and this energy comes out as a very specific radio frequency signal. And these are the signals that the MRI machine is actually listening for. This part is crucial as the timing and the strength of the signals vary depending on the type of tissue. For example, fat and muscle return to their original state at different speeds, and that variation is what allows the MRI to distinguish one type of tissue from another so clearly. So now we move into the signal processing phase. And this is where the signals picked up by the receiver coils are transmitted to a computer system that is able to translate them from pure frequencies into spatial data. And this is done using a mathematical technique called the Fourier transform. So in MRIs, the Fourier transform is a mathematical tool that converts raw data into the images we see as it decomposes the MR signal into its constitute frequencies, allowing for spatial encoding and image reconstruction. Essentially, it transforms the data from frequency space into the familiar image space. Through this process, the computer reconstructs detailed cross-sectional images of the body. So every MRI image we see on a screen is the result of a complex but precise chain reaction, starting with aligning protons, exciting them, detecting their return energy, and turning that data into images.
And thank you for coming to our presentation. Not that you really had a choice, but I hope you really did enjoy it. And here are our citations that we use for this presentation. And thank you, I guess, Quantum Physics for the production of the NMR and MRI. And thank you, Professor, for a great course.